Dear friends, welcome back to another lecture on quantum field theory and quantum entanglement. In the previous lecture, we have been looking at the Dirac Spinors and the solutions of it. So, and then we have seen that in the massless limit, essentially, the equation, the Dirac equation is even without the massless limit, the Dirac equation is sort of not irreducible, it is a reducible representation of the Lorentz group, and that is the reason why we have two components of the Dirac equation. One is the left moving component and the other is the right moving component essentially. But the total number of degrees of freedom of the Dirac equation are 4. For the left moving, you have spin up left moving and particle and right moving antiparticle together forms one spinor essentially, which we call it as U plus, and U minus contains right moving spinor and left moving anti-spinor essentially, anti-particle. Remember that the Dirac equation, each component of the Dirac equation satisfies the Klein-Gordon equation, and that is how you end up having negative energy solutions, and you cannot really, even though the dispersion relationship is linear, the Klein-Gordon because each component satisfies the Klein-Gordon equation, so you end up having negative energy solutions also. So anyway, so coming back to this, we have seen that the Weyl equations come in the limit m goes to 0. Independent of that, is there any way of defining left and right degrees of freedom? For that we introduce this gamma phi. So this gamma phi is defined in this particular fashion. This gamma phi is independent of any representation essentially, in the sense that it has forms, but the chirality component of the gamma phi, meaning 1 plus minus gamma phi, is independent of the representation of the Dirac gamma algebra essentially, algebra matrices essentially. So these projection operators 1 by 2, 1 plus minus gamma phi pick out p plus picks out the left moving component and p minus picks out the right moving component, independent of whether the gamma matrices are defined in chiral representation or in Dirac representation or in Marano representation, any other representation essentially. I will come to Marano representation in a second in something, and various other representations, and each representation one can go from one representation to another by a similarity transformation, and I leave that as an exercise. So then we finally said there is chirality also has a different name, which is called handedness, and the Dirac spinor is decomposed into a left-handed particle and a right-handed particle. Okay. So let us continue with this today. So we will continue with the Dirac spinors today, okay, and their properties essentially. So before moving further, okay, let me just mention a couple of nice properties of the Dirac Lagrangian. So L Dirac psi bar del slash minus m psi has some discrete properties essentially, satisfies some discrete symmetries in particular. There are 3 of them. One is called parity, charge conjugation, and third one is called time reversal. So you have P, C and T, these are the 3 discrete symmetries which satisfies the Dirac Lagrangian, and this is reflected in the solutions also that okay. So these 3 are the symmetries of the Dirac Lagrangian. These are discrete symmetries, these are not continuous symmetries like the previous case essentially. Like space time symmetries are continuous symmetries, like In the Lorentz group, we have seen these symmetries which are associated with rotations, which is and say boost and or translations, rotations or translations. These are continuous symmetry. The boosts are also continuous essentially. They don't form closed form symmetries, but together with rotations they form closed form symmetries, which is this Lorentz group essentially. So, what is time reversal and parity? Okay, let us look at time reversal and parity. We will come to see a bit later. Parity, under parity you have x0 goes to x0 and x bar goes to minus x bar. Okay, or if you want we use xi. Okay, and the space component is inverted essentially with a minus sign, and time reversal is the exact opposite of x0 goes to minus x0 and x bar goes to x bar. Okay, these are the two things essentially. Okay. Now, the time reversal is a very a special property, special transformation, which is anti-unitary operator. It is an operator which is a anti-unitary operator, meaning that means u dagger u is equal to minus 1. Any operator which has, okay, let me call it O dagger O is equal to minus 1 essentially. So, it is not plus 1, it becomes anti-unitary. Okay. So, O dagger is equal to minus O dagger. Okay. Okay. O dagger is equal to minus O essentially, O inverse. So, minus O inverse, that such operators O dagger equal to minus O inverse. Such operators are called anti-unitary operators. So, whereas unitary operators O inverse is equal to O dagger. So, we will come back to that later on if time permits. So, these have a special role, not exactly relevant for our course. As of now, okay, there are very interesting properties of the time reversal and everything, especially for meson decays and so on, so in which the time reversal symmetry is violated and everything. But as of now, for the present course structure of this course, let us not worry about it. We will note that it is an anti-unitary operator compared to any other operators, but let us look at parity. So, parity, what does it do? So, under parity what happens is that under parity left movers become right movers, that means P under P. So, you have things like you under parity what happens is rotations do not change sign, but boost change sign under P. So, rotations do not change sign. Okay. So, you have, so what happens is, now this should be exactly what we wrote the other day essentially, that under boost the left handed and right handed get modified essentially. So, you remember that part essentially. So, under parity this is the same thing which happens. So, you have u plus minus goes to u minus plus, or in psi L goes psi L R goes to psi R L, or any other notation you can think of plus minus goes to psi minus plus under parity. Okay. So, a left handed particle becomes a right handed particle, and given this transformation p square is equal to 1, and then you see that parity is equal to p psi of x t is equal to gamma 0 psi of minus x t. Okay. So, okay. So, gamma 0 is essentially the operator of parity. Essentially gamma 0 is the representation of but what we said that the Dirac Lagrangian is invariant under the parity. Okay. Under invariant is under parity, you can check that, it doesn't matter essentially. So, the Spinor, so psi of x t and p psi of x t both satisfy the Dirac equation. So, that the transformed Spinor also satisfies the Dirac equation. The solution also transforms the Dirac, and this is an exercise essentially. So, you can have an exercise homework problem, you can look into this essentially. Okay. Okay. Now, if you have this bilinear covariance, okay, so you see that under parity, so pi acting on psi bar psi of x t goes to psi bar psi of minus x t. So, so under scalar nothing changes essentially. So, the parity does not really get modified, but for the vectors, vector p acting on psi bar gamma 0 psi x t goes to psi bar gamma 0 psi minus x t, whereas p acting on psi bar gamma I gamma 0 gamma mu is there, so psi bar psi x t is equal to psi bar gamma 0 gamma I gamma 0 psi of minus x t. This picks up a minus sign, the vector picks up a minus sign essentially, like because of the space part essentially, this picks psi bar gamma mu psi. So, the vector picks up a minus sign, and actual vector is one which does not pick up a minus sign. Actual vector will not pick up a minus sign. Okay. So, this the actual, now we have defined gamma 5 p psi bar gamma 5 psi of x t goes to, if you have gamma 5 psi bar gamma 0 gamma 5 gamma 0 psi of minus x t, that goes to minus psi bar gamma 5 psi minus x t. So, this picks up a minus sign because gamma 0 gamma 5 gamma 0 gives you a minus 5, it anti-commutes with gamma. Okay. So, this picks up a minus sign. So, this is opposite to that of the scalar. Say for example, the scalar does not pick up a minus sign essentially, the scalar current. So, the vector current. So, what we have here is a pseudoscalar. Okay. This is called a pseudoscalar. this is the vector, okay, this is a vector and this is a pseudoscalar. Similarly, you can also have an actual vector part of the bilinears, and you will see that this picks up a minus sign essentially. Okay. So, because you can actually calculate it and you see that it picks up a minus sign psi bar gamma phi gamma 0 psi minus x t, and this becomes a plus sign psi bar gamma phi. So, this is exactly opposite to what happens to a vector. So, in vector the space part remains constant, whereas the space part picks up a minus sign, whereas the time part becomes 0, meaning picks up a positive sign. Okay. Now, let me put it this way. Yeah, this is also the space part. So, whereas in the gamma mu in the pseudo axial vector, the space part the time part picks up a minus sign, whereas the space part picks up a plus. It remains positive essentially. So, it does not change really. So, this is all. So, these forms the total bilinears essentially, which are scalar, pseudoscalar, vector, axial vector and tensor, which have 16 components. You can calculate how many components you have and you can compute this thing essentially. Now, why we introduced parity? It turns out that there are some interactions which can violate parity. Okay. There are some interactions like weak interactions which can violate parity. Okay, this is the important thing essentially. We will see. We will not be dealing with them essentially, but there could be interactions. We have not yet started doing interactions with Dirac theory, but we are now setting up the board for it essentially. We are looking up the ground for it essentially. Another class of solutions comes from the C vector. So, for that we need to introduce the C discrete symmetry. Okay. What is the C essentially? C is charge conjugation symmetry. So, what does it do? Psi C is equal to C psi star. So, okay, I did not come to the solutions. What it does, this charge conjugation symmetry. So, this symmetry has several properties. At the basic point, it takes particles to antiparticles, and in Dirac picture it can be used to find real solutions of Dirac equation. So, if you ask, the solutions of Dirac equation are complex, as you know very well essentially, and Okay, we will also just for confirmation we will just do it in a couple of in soon essentially. But if you want to find, say that are there any solutions of the Dirac equation in which all the gamma matrices are imaginary and so the solutions of the Dirac are real, you need this matrix in which the charge conjugation of psi I is equivalent to defined in this particular fashion essentially. So, the complex conjugation times this matrix C. This matrix C satisfies C dagger C is equal to 1 because it should be unitary, and C dagger gamma mu C is equal to minus gamma mu whole star. Okay, psi bar gamma mu C is equal to this. It is a unitary 4 by 4 matrix, 4 by 4 matrix which is unitary. Okay, it is unitary. Unitary means A dagger A is equal to 1 or okay, such thing essentially. Now, okay, now psi, now if you want to ask the question, if psi is equal to psi c, are there any solutions when psi is equal to psi c, where psi c is equal to c times psi star essentially. Okay. So, this is the definition essentially, c is equal to psi c is equal to c times psi star. This brackets I think redundant, let us just not put it. So, if I put the condition psi is equal to c times psi star, are there any solutions of the Dirac equation essentially? So, under Lorentz transformation psi c transforms exactly the same way as psi essentially. Okay. Now, let us look at the condition that let psi c, it can be shown, actually it can be shown psi c also satisfies the Dirac equation. So, how do you show that? That means you start with you do the full charge conjugation I del slash minus m psi is equal to 0. This implies minus psi del star minus m psi star is equal to 0. Okay. This is just a conjugation essentially. So, this is equal to c minus I del star minus m psi star is equal to plus I del slash minus m psi c is equal to 0. Okay. So, how did I get this the second equation? Because I can use meaning if I impose the c, so imposing the c I del slash minus m, if I, because I can impose the c on the left hand side, the right hand side is 0, I can impose c both sides essentially. So, you end up having the same Dirac equation, okay, on both sides essentially. So, impose c, so applying multiplying with c on both sides gives me c I del slash minus m psi star is equal to this. This is nothing but I del slash. Okay, there is a slash. Okay, so this c and del slash it will just make it positive, and minus c psi star is nothing but your definition of psi c. So, psi c also satisfies the Dirac equation. So, if I impose the condition that psi is equal to psi c, you have conditions for the reality of the Dirac spinor. If psi is equal to psi c, then the wave functions of the Dirac equations are real. Okay, we will see the physical significance of it in 1 or 2 minutes essentially. Okay, this is the main thing, that psi is equal to psi c will imply. So, this gives me this condition. So, what are the gamma matrices? Which lead to this possibility. Okay, what is the Majorana? This is called the Majorana basis. What is the gamma matrix basis? Okay, in which this is possibility. So, this is the basis in which gamma 0 is equal to 0 sigma 2 0, gamma 1 is equal to I gamma 3 I sigma 3 times I sigma 3, gamma 2 is equal to 0 minus 2 0, and gamma 3 is equal to minus I sigma 1 0 0 minus I sigma 1. Okay. So, now you see this is a basis of gamma matrices where all of them are real. Okay. So, that means the gamma matrices are real, or are imaginary. What did I say? Okay, I said the opposite actually, are completely imaginary. So, this is a basis in which of the gamma matrices, all the gamma matrices are completely imaginary. What it means is that you remember that the Dirac spinor is complex numbers, essentially there are 4 degrees of freedom, 8 complex numbers. Now, you have reduced the number of degrees of freedom to half. This reduces the number of degrees of freedom of Dirac spinor by half. Okay. So, initially you have 4 degrees of freedom, it reduces to 2, essentially 4 degrees of freedom goes to 2 degrees of freedom. Okay, yeah. So, this is the point. Now, you should also realize that once the gamma matrices are all imaginary, what it means, the generators of the group are all real. So, S of lambda are all real. So, the Dirac equation is real, okay, because Dirac equation is I del slash minus m. So, gamma is real, and the generators of the group S of lambda is 1 by 2 gamma mu I by 2 gamma nu all of them become completely real, the Lorentz transformations are real. Okay. So, the basis of this is completely real. So, the spinorial the basis vectors which span this gamma matrices is nothing but a real spinor degree essentially. So, this is a real spinor psi is equal to psi star, and such spinors are called Majorana spinors. So, just to make difference I put a m. Okay. This is a real spinor. So, psi m is equal to psi m star essentially. These are such spinors are called Majorana spinors essentially. Okay. Now, in terms of the Dirac spinors, what is the condition this? In terms of the Dirac spinors, we have Dirac solutions essentially. You have this u plus u minus essentially. You have this Weil spinors u plus u minus. So, what is the Majorana spinor in terms of the Dirac spinor solutions? U plus u minus solutions or chiral solutions of the Dirac spinor. You should remember that Majorana spinors are a completely different object. So, they are only two component Majorana spinors, they are completely different. Okay. Okay, but if you want to write them in terms of the 4 component Dirac spinors, so what happens is that you can write them. So, Dirac spinors are complex and they are not real, and they will have 4 degrees of freedom. But you can express Majorana spinors in terms of Dirac spinors. So, so if you define the C matrix, the C matrix will turn out to be I gamma 2 in chiral basis. In fact, I gamma to gamma 0 essentially it will just become, and this is just 0 minus I sigma 2 0. Okay, the C matrix. Under this transformation you should have psi C is equal to C psi star is equal to psi. This is the condition in chiral basis. So, under this transformation you will end up having u plus is equal to I sigma 2 u minus star, u minus is equal to I sigma 2 u plus star. So, this u plus and u minus are no longer independent, they are the same. So, this same for Weil spinors also, what we say essentially for Weil spinors, chiral spinors or Dirac spinors essentially this is the same, essentially they are no longer independent if the Majorana condition is imposed. This is the Majorana condition. So, this okay, this is the Majorana condition is imposed. You start with Dirac spinors, but if you start directly with a Majorana basis, okay, if you start directly, in that case it is a 2 component real spinor essentially. So, in this case you have psi is equal to, let me put in Majorana thing, 4 component Majorana spinor. So, this is a 4 component Majorana spinor. Okay. So, we have learnt about Majorana spinors. We have seen how these various symmetries C and P will help us understand the solutions essentially. And in the next class we will actually write down the solutions of the Dirac equation, just to remember ourselves essentially what are these solutions essentially. Okay. So, one important class of solutions is the Majorana spinors, which are essentially taking you which make the left spinor not to be not independent of the right spinor essentially. In other words, the Majorana condition, the Majorana we will see in a Majorana condition implies particle is equal to antiparticle. Okay. The Majorana condition reduces the degree of freedom by half by imposing that the particle should be equivalent to its antiparticle essentially. So, the particle will be equivalent to its antiparticle. Now, you can write directly in terms of the Majorana spinors, which are 2 component real spinors essentially, or you can write in terms of the Weil spinors, the same matrix, which will give you 4 component Majorana spinors, in which a U minus part is no longer independent, but is given in terms of the U plus itself essentially. Okay. So, this maybe there is a star missing. Okay. So, this tells you that the number of degrees of freedom is reduced, and as we will see that while chiral spinors represent a particle which is moving in the left hand direction and an antiparticle moving in the right hand direction, and the right chiral spinor represents 2 component 1, which represents a right moving particle and left moving antiparticle, both of them. But the Majorana condition, what does it do? It says that the left moving and right moving particle spinor solutions are no longer different. There is an, because the antiparticle is equal to particle essentially. So, you independently have only one condition essentially. So, the particle and antiparticle are the same. So, this condition reduces the number of degrees of freedom. You only have either left moving or right moving. So, there is no longer because the particle and antiparticle are the same. So, you do not have this extra degree of freedom. So, that kind of spinors are called Majorana spinors essentially. Okay. So, let me stop here, and in the next class we will look into the solutions of the Dirac equation and we will proceed further essentially. Okay. Thank you very much. Yeah.